All right, so chapter 2, part 4. Let's talk about the term molecules versus the term compounds. Molecules are two or more atoms that are chemically combined to form a structure that behaves as an independent unit. It can be a combination of the same atom, like oxygen. Oxygen in the air is O2, or it can be something that has different atoms in it, like water, H2O. Compounds, however, have to have different types of atoms that are chemically combined. Now, H2O still fits that because you've got hydrogen and you've got oxygen, but the oxygen that you find in the air, that O2 I was talking about, is not a compound because you've got the same atoms instead of different ones. What that ultimately means is not all molecules are going to be compounds, okay? The kinds and numbers of atoms in a molecule or compound can be represented by a chemical formula, denoting chemicals by symbol and number subscript. You already know this if you know H2O, because here are my symbols, here's my number subscript. That has not changed. Glucose is another example of this. You've got C6H12O6. Ultimately, what that means is you have 6 carbons in there, 12 hydrogens, and 6 oxygens. That's what that chemical symbol number subscript means. Molecular mass is adding up the number of adding up the molecular mass of all of the atoms. So, for example, with C6H12O6, you wouldn't say it's 1 carbon, 1 hydrogen, and 1 oxygen. You would have to get the molecular mass for carbon. Give me 1 second, which is 12.011. Okay, I'm going to write this down. So carbon is 12.011. Oxygen is 15.9944, I think. Yeah, that's how horrible my eyesight is. And hydrogen is 1.007. I'm going to go with 5. Okay, so how many carbons do I have in this molecule? I have 6, right? So it would be 12.011 times 6 plus hydrogen. I've got 12 of them. Well, that was 1.0075 times 12. That is just way too small, right? I'm sorry, guys. Okay. So I have 6 carbons, right? I have 6 carbons because it's C6H12O6. So 6 times 12.011 plus I have 12 hydrogens. So I have 12 hydrogens, and the number that was there for my molecular mass was 1.0075 plus I have 6 oxygens, so it's 6 times the molecular mass of 15.9944. Okay? You got to kind of think of it as I've got 6 cars, 12 pillows, and 6 bed frames. If you want the mass of that, you have to take into account that there are 6 cars, 12 pillows, and 6 bed frames. You can't say, I'll add up the mass of 1 car, 1 pillow, and 1 bed frame, and it'll be exactly the same. You do have to take into account that with this, you're talking about multiple atoms, so you do have to kind of calculate that up. Now, intermolecular forces. That prefix, hang on a second. Inter Not sure why my pen stopped working. There we go. Means between. Intermolecular, in between the molecule forces. It's the result of weak electrostatic attractions between oppositely charged parts of molecules or between ions and molecules. These are much weaker than chemical bonds. So this is actually water. Remember that in water, our oxygen and our hydrogen had those partial charges. So we had partial positive near the hydrogen and we had partial negative near the oxygen, right? So that partial positive here is attracted to that partial negative here. This partial positive here is attracted to that partial negative right there. That type of bonding is called an intermolecular force because we've got that difference in charge within the same molecule. Now, when hydrogen is bound to anything else, it doesn't matter. As long as it's not another hydrogen, there's always going to be that difference in charge, okay? There's always going to be an unequal amount of protons on the opposite side of that bond if it isn't a hydrogen. So when you've got hydrogens doing this kind of intermolecular force bonding, we call them hydrogen bonds, okay? Now, normally these are very, very weak bonds. So imagine I take one strand of hair from your head and I yank it really, really hard. What's going to happen? Hair's going to break, right? But if I take all of your hair and I put it in one big ponytail and I yank it really hard, what's going to happen then? I'm going to yank the tar out of your head, right? Individually, these types of bonds are very, very weak. They don't really do much. They're weaker than the chemical bonds, the ionic bonds and the covalent bonds. But when you put them together, they can actually become fairly strong. As well, depending on what molecule you're talking about, they can actually cause it to fold the way that we need it to fold. So everybody knows the shape of DNA, right? That double helix, that twisted ladder that we see whenever we see DNA. Those bonds in between those two sides of the ladder are actually hydrogen bonds. Those are the bonds that are holding this DNA together. So again, if it's individual, it's like pulling a hair out of somebody's head. But when you've got dozens and dozens of them, it can actually work really well and it can give something its shape. Now, this is the other thing with that. It can give something its shape and allow us to pull it apart fairly easily if we need to. Again, that's fairly easily, not necessarily easy. All right, so the intermolecular forces, again, weak electrostatic attractions between oppositely charged parts of molecules, between ions and molecules. These are much weaker than chemical bonds. Ionic covalent, they're leaps and bounds better if we're talking about stability. Now let's talk about solubility and dissociation. Solubility is the ability of one substance to dissolve another. So a good example of solubility is putting sugar in water. When you put sugar in water, it dissolves. So it has a high solubility in water. Oil in water, not so much. It doesn't have a good solubility because oil doesn't dissolve in water. So, charged or polar substances will easily dissolve in water. Remember that partial positive, partial negative nature of water will take things that actually have charge, like sodium and chloride, and actually split them apart. When you put salt in water, that positive charge gets surrounded by the partial negatives of the oxygen in water. That partial negative charge in chloride gets surrounded by these partial positive hydrogens in water. So when you put salt in water, it actually falls apart, and you've got sodium kind of suspended inside of water molecules, and you've got chloride suspended in the water molecules as well. Nonpolar substances, again, let's go with oil. They don't dissolve in water. Okay. Ionic compounds, they will dissociate, they'll separate because the cations will be attracted to the negative, and the anions will be attracted to the positive, just like what we see over here. Although molecules do not dissociate, one molecule can be surrounded and thus suspended in water. So, for example, sugar actually is a ring structure. Okay? That ring structure has positives and negatives around it. And it's this whole thing that actually gets suspended. It's not necessarily the individual atoms, but does it still break apart in water from the crystals that you have in your sugar bowl? Yes. So we still say that it is actually soluble, it dissolves. Electrolytes. So I'm sure anybody who's ever seen a Gatorade commercial has heard of electrolytes. Replace your electrolytes. I never understood what that meant. I was like, okay, so what's an electrolyte? It's actually cations and anions that can conduct current. That's why they call them electrolytes, because they will actually conduct current, but they are charged so that they can carry that current. So chemical reactions and energy, synthesis reactions, decomposition reactions, reversible reactions, oxidation reduction reactions, and energy. Okay, chemical reactions. Atoms, ions, molecules, or compounds will interact with each other to form or break chemical bonds. If I want to make a sugar or break down a sugar, those bonds have to be changed. And no matter which type of chemical reaction you're talking about, it doesn't matter. You have two major players. You have the reactants and you have the products. And it is all based on position. So here's my arrow showing my chemical reaction. Here's my arrow showing my chemical reaction, right? If I am before that arrow, I am a reactant. If I am after that arrow, I am a product. And if you actually look at both of these chemical reactions, they are the same reaction. It's just going in reverse, basically. I have ATP, I'm breaking it down into ADP, phosphate, and energy. So here's my reactant, it's before my arrow. Here's my products, it's after my arrow, right? Now look, I have ADP, phosphate, and energy, and I am making ATP. In this case, because these are before my arrow, I would call them the reactants. And over here, my ATP would be the product because it's the end result of the reaction. Keep it simple. I'm not looking for chemists because that isn't what this class is, but just realize what enters a reaction is a reactant. What results from that reaction is a product. There are three important points to all chemical reactions. Okay? I can take something that is simple or less complex and combine it into something that is more complex. So I can take the building blocks of proteins, which are relatively simple amino acids, and I can put them together like Legos and build a very complex protein. So I can take individual Legos and I can build the Death Star. Okay? Now, another way for this to go is for me to take the reactant and break them down into simpler, less complex molecules. So I can take that Death Star made out of Legos and I can take it apart and get individual Legos from that. So we can go either direction. I can go from simple to complex or complex to simple. Now, this is the big thing. Atoms are generally associated with other atoms through chemical bonding or intermolecular forces. So no matter which one I do, one or two, I'm going to have to change the relationships between those atoms. If I take the Death Star made out of Legos and I pull it apart into individual Legos, I'm changing how those Legos are interacting with each other. It isn't more complicated than that when it comes to atoms. If I want to change how a compound is put together, those bonds have to change as well. So, synthesis reaction. What does it mean to synthesize something? It means to create. Okay? So, it's when two or more reactants chemically combine to form a new larger molecule. So I'm taking something simple, individual Legos, and I'm making something complex, the Death Star. We can also call this a dehydration reaction. That is another name for this. So what does it mean to be dehydrated? What are you losing? You're losing water, right? If you look at this reaction up here, I've got OH and H, and I'm basically taking those out to create water. And when I do, I take this chunk here and this chunk here, and I glue them together. So I'm taking two simple amino acids and gluing them together to make something bigger, and I'm taking water out. Now, are all synthesis reactions dehydration reactions? Technically, no. But if you know the meaning of the word, you know what's happening in the reaction. So, old chemical bonds are broken, new bonds are formed as the atoms are rearranged. Now, if you look at this, I'm taking something simple and I'm making something more complex, right? This is called anabolism. When you build something, it's called anabolism. Growing, when your bones are growing, when your muscles are growing, when you're doing maintenance. Let's say I worked out and I accidentally tore one of my muscles a little bit and I need to fix it. Repair, I got stabbed in the arm and I need to make scar tissue. All of these are anabolic reactions because I'm making something more complex. I'm not breaking something down, I'm synthesizing something, I'm making something more complex. Now, a decomposition reaction. What does it mean to decompose? To break down, right? So, decomposition reactions are basically the reverse of a synthesis reaction. You've got something big and complex, a large reactant, and it's chemically broken down into smaller products. So I am now taking the Death Star and I'm making it into Legos. I'm taking something big and complex and I'm breaking it down into something smaller and more simple. You can call this a hydrolysis reaction. Hydro means water. Lysis means to break. So hydrolysis, I'm going to use water to break something. So if you look, here's my H2O, right? I've got two H's and an O. When you look at the actual reaction, I've got an H over here and an OH over here. There's my water, but I took this and broke it apart into part A, or 1, and part 2, right? So hydrolysis, when you use water to break apart components. This is called catabolism or catabolism, okay? It's used when you break something down. So catabolism, I always think of my cat Mischief. Mischief, if there were any papers on the floor, didn't matter if it was a catalog, a magazine, students' papers, it didn't matter. If it was on the floor, she would take her claws and she would rip it to shreds. Her back claws specifically, as if she was trying to cover up litter. Don't ask, I don't know why. But catabolism is to break down, it's not to build. Now, you've probably heard the term metabolism. Yes? Metabolism is both catabolism and anabolism. It's all of the chemical reactions that happen in the body. So we're talking building and we're talking breaking down. It's kind of the umbrella term to describe both halves. Okay? Now, a reversible reaction is exactly what it sounds like. It's a chemical reaction that can go forward or it can go backward. And honestly, the easiest way to tell it's a reversible reaction is looking at that arrow. If you've got a double-headed arrow going in both directions, you know it's a reversible reaction. Now, this is kind of the interesting thing with reversible reactions. It's about equilibrium. I want to have the same number of molecules on this side as I do on this side. If you think of the old school scales where you had the two platforms and you had to get them so that they were both equal on both sides, that's kind of what a reversible reaction is. If you have too much on this side, it'll start breaking stuff down so that you have the same number on this side as this side. If you have too much on this side over here, it'll do the exact same thing. It'll start building this molecule on the other side so that you have the same number of molecules on one side as the other. It is literally all about equilibrium. In your body, you've got this kind of balance. We talked about homeostasis, right? There has to be balance there. Now, an oxidation reduction reaction. Another chemical term. Remember oil rig, because ultimately oxidation and reduction reactions are talking about either gaining electrons or losing electrons. And depending on which one you do, it tells you which reaction you are. So oxidation is loss. That's where oil comes in. Oxidation is loss. Reduction is gain. Rig. R-I-G. So if I'm going through an oxidation reaction, if I'm a chemical going through an oxidation reaction, I'm losing electrons, just like sodium did in our ion example. If I am getting reduced, if I'm going through a reduction reaction, I'm gaining electrons. I'm getting extra electrons, like chloride did. Now, something that is interesting, the ionic oxidation reduction reaction that we did for the ionic bond means that we are completely losing or we're completely gaining. We're not doing the sharing thing, okay? Covalent is partial because I have it sometimes, I don't have it other times, but I'm not completely giving it away either. We're sharing. Now, something else that's kind of interesting, most of the time we call these redox reactions. We don't really refer to them as oxidation only or reduction only, because if you've got one, you tend to have the other. It's not necessarily stable just to have one. So if you have one, you have the other, so they kind of go together. So when chemists talk about these types of reactions, we just refer to them as redox reactions. Synthesis and decomposition reactions can be redox reactions, just so you're aware. Now, chemical reaction and energy. Remember, E with a plus is just my abbreviation for energy. Energy is the capacity to do work. There are two classifications of energy. One is potential energy. When somebody says, oh, but they have so much potential, what does that mean? It means that they could do it, but they're not doing it right now, right? So potential energy is a stored form of energy. It can do work, but it's not doing it right that second. So your book mentions holding a ball in your hand. Can the ball fall out of your hand? Technically, yes. And gravity technically is pulling on that ball, but is it going anywhere right now? No. So it has the potential to fall, but it's not falling right now. When we talk about sugar and things like that are stored form of energy. Technically, if I eat that sugar, my body can actually do work. But right now, if it's sitting, let's say, in a candy wrapper on my desk, it's not doing it right then. It's potential energy. Kinetic energy is actually the form of energy that does work or moves matter. So if I drop the ball and the ball is actually falling from my hand to the ground, that's kinetic energy. It's moving energy. If you've ever heard of kinesiology, right? PE, physical education, is kinesiology. The reason that they call it kinesiology is because it's the study of movement. It's that energy that's moving matter, okay? So if I were to eat the candy bar on my desk and move my muscles around, that would be kinetic energy, moving my muscles. So those are the two classifications. Now, those two types I just mentioned actually come in three forms. There's mechanical energy, chemical energy, and heat energy. Mechanical is pretty easy. Mechanical is energy that results from the position and movement of objects. So moving a limb is a good example of mechanical energy because physically there is something switching positions. Okay? Chemical energy is a form of energy in which a substance is a form of stored energy within its chemical bonds. Snickers bar. If you are hungry, let's say you're hangry, right? There was that campaign by Snickers, here, have a Snickers, right? You're not yourself when you're hangry. Yes? Okay. Within the bonds of the Snickers bar, the sugar molecules and those types of things, there is stored energy, and that's chemical energy. Because in order for me to get to those bonds, I have to do chemical reactions in my body. And then finally, we have heat energy. It's energy that flows between objects that are different temperatures. So the best way I can think to describe this, it's a very, very cold winter's day. You go and you get hot chocolate, and what's the first thing you do with that cup? You put it in between your fingers and you go, ha, 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 right? What happens? The heat from the cup transfers to your fingers. So it's a flow of energy between objects of different temperatures, the hot cup to your cold fingers. Same kind of thing. It's hot in South Texas. Hello, where do we live? And you have a cold bottle of water and you're outside working and you take that cold bottle of water and put it up against your neck and put it on the back of your neck, and the heat from your body gets transferred to the cold of the bottle, right? Now, technically, the cold isn't transferring. Your heat's just getting sucked out. So that's heat energy. Okay, so the speed of chemical reactions. You know what? I'm going to put this into another lecture.